Let's be clear about what we're talking about. Are there aliens out there, life on other planets? I don't know. Maybe there is, maybe there isn't. That's not what I'm saying. What I'm saying is much more specific. Even if they exist, even if there are millions of civilizations out there in our galaxy right now, they're not going to arrive here. And we're not going to go there either. And it has nothing to do with whether they exist or whether they're smart or whether they have technology. It has to do with something much more fundamental. Let me start with a story. In 1950, I was at Los Alamos with some other physicists, Edward Teller, Emil Konopinski, Herbert York, and we were talking about flying saucers. This was when flying saucers were in all the newspapers, you understand. People were seeing them everywhere. And we were having lunch, walking to the cafeteria, and we were talking about whether it was possible for aliens to travel faster than light, whether they could visit us, all of this stuff. And then I asked, in the middle of lunch, I just blurted out, where is everybody? You see, I had been thinking about the numbers. The galaxy is old, very old, about 10 billion years. And it's big, very big, 100,000 light years across. And there are maybe 200, 300, 400 billion stars in it. So I did a little calculation on a napkin. If you had a civilization and they built some rockets, not even very good rockets, just atomic rockets, they could get to the nearest star in maybe 10 years. And then from there, they spread to the next stars and so on. And you know what? Even doing it slowly, hopping from star to star, you could colonize the entire galaxy in maybe 10 million years, maybe 100 million years if you're really taking your time. Now, 10 million years sounds like a long time to you and me, but the galaxy has been around for 10,000 million years. That's 10 billion years. So if there was a civilization that started anywhere in the galaxy, even 1 billion years ago, they should be everywhere by now. They should have gotten here a long time ago. So where is everybody? This is what people now call the Fermi Paradox, though I never called it that. I just asked a question. But it's a good question. And the answer, I think, is actually quite simple when you look at the physics. Let me explain to you what the problem is. The problem is space, just space, the emptiness, the distance. People don't appreciate how far apart things are. They really don't. Let me give you an example. The nearest star to us, not the sun, but the next one, is called Proxima Centauri. It's about 4¼ light years away. Now, what does that mean? Light travels at 186,000 miles per second. That's fast. Nothing goes faster than that. We'll come back to that in a minute. So light from Proxima Centauri, traveling at this incredible speed, takes 4¼ years to get here. Now, we've built some pretty fast spaceships. The fastest thing we've ever made is the Parker Solar Probe, which goes about 430,000 miles per hour. That's fast by our standards. But you know how long it would take to get to Proxima Centauri at that speed? About 7,000 years. 7,000 years. That's longer than all of recorded human history. But Feynman, somebody says, that's with our primitive technology. An advanced alien civilization would have much better rockets. Okay, fine. Let's imagine they have fantastic rockets. Let's say they can get up to 1/10 the speed of light. That's phenomenally fast. That's about 67 million miles per hour. Nothing we've built is even close to that. And at that speed, it would still take 42 years to get to Proxima Centauri. 42 years! And that's just to the very nearest star. Most stars are much farther away. The average distance between stars in our neighborhood of the galaxy is about 5 light years. To get to a star that's, say, 1,000 light years away, even at 1/10 the speed of light, would take 10,000 years. Think about that. 10,000 years ago, we were just figuring out agriculture. We didn't have writing. We didn't have cities. And you expect a civilization to maintain a space program for 10,000 years just to send somebody to one star. Now you might say, well, what if they go faster? What if they go half the speed of light or 90% the speed of light? Okay, but now we run into a different problem. It's not just that it's hard to go fast. It's that the faster you go, the more dangerous it becomes. You see, space is not empty. It's nearly empty, but not quite. There's about 1 atom per cubic centimeter in interstellar space. That doesn't sound like much, does it? But when you're going at a significant fraction of the speed of light, even hitting 1 atom is a big deal. Let me explain why. Imagine you're in a spaceship going at 1/10 the speed of light, and you hit a grain of sand, just a tiny little grain of sand. Do you know what happens? The energy of that collision is equivalent to a nuclear bomb. Not a little bomb, a big bomb. 1 grain of sand. And there's lots of stuff floating around in space. Micrometeoroids, dust, little chunks of ice, all sorts of debris. If you're going fast enough, any one of them could destroy your ship. Well, someone says, just put shielding on the ship. Okay, fine. You want shielding? Let's figure out what you need. To protect against high-speed collisions, you'd need something really thick, maybe a meter of water all around the ship, or several meters of some other material. Do you know how much that weighs? It's enormous. And now you have to accelerate all that mass to 1/10 the speed of light. The amount of energy you need becomes, it becomes absurd. Let me give you some numbers. To accelerate just 1 kilogram, that's about 2 pounds, to 1/10, the speed of light requires about 450 trillion joules of energy. That's about the same amount of energy that the entire United States uses in 5 seconds for 1 kilogram. Now multiply that by the mass of a spaceship with all its shielding, life support, fuel, crew, everything. You're talking about more energy than the sun produces in years. Where are you going to get that energy? How are you going to generate it? How are you going to store it? But Feynman, someone says again, what about antimatter? What about fusion? What about something we haven't discovered yet? Look, antimatter is real. We can make tiny amounts of it in particle accelerators. But to make enough antimatter to fuel an interstellar ship would require, we're talking about converting a significant fraction of a planet's worth of matter into energy. It's not practical. It's not impossible in principle, but it's not practical. Fusion, we've been trying to make fusion work for 75 years, and we still haven't built a fusion reactor that produces more energy than it consumes. And even if we do, using it for rocket propulsion is a whole different problem. The energy densities are just barely at the threshold of what you'd need. What about something we haven't discovered yet? Okay, this is where we have to be very careful. People like to say, well, 200 years ago, nobody knew about nuclear energy, and now we have nuclear power plants. So who knows what we'll discover in the future? Now, this is true, but there's something you need to understand about physics. In the 19th century, there were lots of things we didn't know. We didn't understand atoms, we didn't understand relativity, we didn't understand quantum mechanics. We've learned a lot since then. But here's the key point. The things we've learned have not made new things possible that we thought were impossible. They've mostly confirmed that things we thought were impossible really are impossible, but for different reasons than we thought. Let me give you an example. Before Einstein, people thought that maybe if you went fast enough, you could exceed the speed of light. Einstein showed us that no, you can't. The speed of light is not just a speed limit. It's built into the structure of space-time itself. Mass, energy, space, and time are all connected, and as you go faster, you need more and more energy to accelerate, and at the speed of light, you would need infinite energy, so that's out. What about warp drive? What about wormholes? I'm glad you asked. Let me tell you about these things because they're very interesting, but they're not going to save us. A warp drive, the idea is that instead of moving through space, you warp space itself. You compress the space in front of you and expand it behind you, and you surf on this wave of space-time. It's a beautiful idea, and it's not ruled out by Einstein's equations. But, and this is a big but, to make it work, you need something called exotic matter. This is matter with negative energy density. Now, what does that mean? It means it has less than nothing, not just zero energy, but negative energy. Does such a thing exist? We don't know. We've never seen it. We can write it down in equations, sure. We can say, if exotic matter exists, then you could make a warp drive. But that's like saying, if I had some magic beans, I could grow a beanstalk to the sky. It's consistent with the mathematics, but that doesn't mean it's real. What about wormholes? Same problem. To keep a wormhole open, to prevent it from collapsing, you need exotic matter, lots of it. And even if you could somehow make a wormhole, you'd still have the problem of getting to the other end to set it up in the first place. You see, this is what people don't understand. These ideas, warp drives, wormholes, they're not just advanced technology. They require things that probably don't exist in nature. They require us to completely rewrite the laws of physics as we understand them. And while I'm always willing to admit that we might be wrong about something, the things we'd have to be wrong about are very fundamental. They're the things we've tested millions and millions of times, and they always work exactly as we expect. Now let me tell you about another problem that nobody talks about much, but it's a real killer: time. Even if you could build a ship that could get up to a reasonable fraction of the speed of light, And even if you could protect it from collisions, and even if you could power it somehow, you still have the problem that the trip takes a long time. From the perspective of the people on the ship, maybe not so long because of time dilation. If you're going fast enough, time slows down for you. But from the perspective of the civilization that sent you, decades, centuries, maybe thousands of years. Do you know what happens to civilizations over thousands of years? They collapse, they change, empires rise and fall, languages evolve, technologies become obsolete. The people who sent the ship will be long dead. The civilization might not even exist anymore. Who's going to fund a space mission where the result won't come back for 10,000 years? And here's another thing. What are you going to do when you get there? Let's say, miracle of miracles. You make it to another star system. You've spent centuries traveling. Or maybe you've been in some kind of suspended animation, which we also don't know how to do, by the way. You get there. And what do you find? Most likely nothing. No planets in the habitable zone. Or planets, but no life. Or life, but not intelligent life. Or intelligent life, but they're still at the level of bacteria or fish or something. The chances of finding another civilization at approximately your level of technology at the exact moment you arrive are incredibly small. You've spent all this effort, all this energy, all this time, and for what? Now, I know what you're thinking. You're thinking, but Feynman, what if there are millions of civilizations out there? With millions of civilizations, surely some of them would have made the trip. And this brings me to what I think is the real answer to my question from 1950. Let me ask you this. If you were an advanced alien civilization and you had the resources to maybe, just maybe, send one ship to another star system at enormous cost and with a very low probability of finding anything interesting, would you do it? Or would you stay home and use those resources for something else? You see, this is what people miss. They think about interstellar travel in terms of, can it be done? And the answer is, maybe in principle, if you're willing to spend an enormous amount of resources and accept enormous risks and wait an enormous amount of time. But the real question is, should it be done? Is it worth it? And I think the answer is probably not. If you're an advanced civilization, what you really care about is staying alive, staying comfortable, learning new things, exploring, yes, but maybe exploring in other ways. You can learn a lot from telescopes. You can send robots, small, cheap robots that don't need life support. You can do computational science, run simulations, explore mathematical spaces. Why would you send biological organisms across the galaxy when it's so difficult and expensive? This is sometimes called the radical mundanity hypothesis, though that's not my term. Somebody made it up recently. The idea is that the reason we don't see aliens isn't because of some dramatic catastrophe or some great filter that wipes out civilizations. It's much more boring than that. It's just that interstellar travel is hard and not particularly rewarding, so nobody does it. Think about it this way. On Earth, we could send expeditions to the bottom of the ocean, the deepest parts, and occasionally we do, but we don't have colonies there. We don't have cities there. Why not? Because it's hard and expensive and not particularly useful. The same thing applies to space, but multiplied by 1 billion. Now, what about communication instead of travel? This is a better question. Communication is much easier than travel. You don't have to send a ship, you just send a signal. Light travels at, well, the speed of light. So if there's a civilization 100 light years away and they send us a signal, we could receive it in just 100 years. That's not so bad. Except there's a problem here too. The galaxy is 100,000 light years across. If you send a signal, it takes 50,000 years to get halfway across the galaxy, and then another 50,000 years for a reply to come back. That's a 100,000-year conversation. What civilization stays interested in a conversation for 100,000 years? And that's assuming they're even sending signals at all. Why would they? Broadcasting into space uses energy. It alerts anyone who might be listening to your presence, and maybe that's dangerous. If you were a civilization, would you want to advertise your presence to the entire galaxy? Maybe there's something out there you should be afraid of. This is the dark forest hypothesis, that civilizations stay quiet because it's safer. Or maybe, and this is what I think is more likely, maybe they just don't bother, because what's the point? You send a signal, and maybe in 1,000 years you get a reply, and maybe you don't. It's not a very exciting research program. Here's what I think is really going on. I think there probably is life out there, maybe lots of it, maybe some of it is intelligent. Maybe some of those intelligent civilizations develop technology, but they're all stuck in their own solar systems, just like we're stuck in ours, because the distances are too great, and the energies required are too large, and the time scales are too long, and the benefits are too small. We're all alone, not because we're the only ones who exist, but because we might as well be. We're separated by distances so vast that we can never reach each other. We're like islands in an infinite ocean, each one inhabited, each one developing its own civilization, but never able to build a bridge to any other island because the ocean is too wide and the storms are too fierce. Is this depressing? Maybe, but I don't think so. I think it's actually quite beautiful in its own way. Each civilization, each instance of intelligence arising in the universe is unique, precious. We're not going to be invaded. We're not going to be saved by wise aliens. We're not going to join some galactic federation. We're on our own. We have to solve our own problems. We have to figure out our own future. And you know what? I think that's okay. We've got a whole solar system to explore. There are hundreds of moons, thousands of asteroids. There's plenty to do right here in our own cosmic backyard. We don't need to go to other stars to have a future in space. But people don't like this answer. They want the science fiction dream. They want the warp drive and the alien civilizations and the galactic adventures. And I understand that. It's exciting. It's romantic. But science isn't about telling you what you want to hear. It's about telling you what's true as best as we can figure it out. Could I be wrong? Of course. I've been wrong before. Maybe there's something we don't understand about physics that makes interstellar travel easy. Maybe exotic matter is real and common. Maybe there's some trick with quantum mechanics that allows for instantaneous communication or travel. Maybe. But based on what we know now, based on well-tested physics, based on the actual distances involved, based on the energies required, the conclusion seems pretty clear. The aliens, if they exist, are staying home. And we're staying home too. We're all trapped in our own little corners of the galaxy, looking up at the stars and wondering if anyone else is out there, also looking up, also wondering. And you know what the funny thing is? Even if I'm wrong, even if someday, 1,000 years from now, we figure out how to travel to the stars, it still won't matter for the Fermi Paradox, because the paradox is about now. It's about the fact that the galaxy has been around for billions of years, and if interstellar travel were easy, somebody should have gotten here by now. The fact that they haven't tells us something important. It's not easy. It might not even be possible in any practical sense. So when people ask me, when will the aliens arrive? I tell them they won't. They can't. Not because they don't exist, but because the universe is too big and the stars are too far apart and the laws of physics are what they are. We're alone, not because we're special, but because everyone is alone. And that's the reality check. The universe doesn't care what we want. It doesn't care about our science fiction dreams. It just is what it is. And we have to deal with it as it is, not as we wish it were. That's what physics teaches you. That's what reality teaches you. And honestly, I think dealing with reality, understanding how things actually work rather than how we wish they worked, that's more interesting anyway. The real universe is more subtle, more complex, more surprising than any story we could make up. We just have to be willing to accept what it's telling us. So there you have it. That's why the aliens will never arrive. Not because they hate us, not because they don't exist, not because they're hiding, but because they can't. Because space is vast, and travel is hard, and time is long, and energy is precious. Because the universe, for all its wonders, has rules. And those rules, as far as we can tell, make it essentially impossible for different civilizations to ever meet. Where is everybody? They're at home, same as us, and that's where they'll stay.